In this video, I want to introduce the notions of work and energy. All right. For a long time, people had an intuitive notion of something called energy. When we think of, if I asked you to think of, what do you think of when you think of something that has a lot of energy? Maybe you think of an Olympic sprinter, maybe a 2-year-old toddler, okay, maybe a bomb, okay, dynamite, right? Those are some things that might occur to you, something moving quickly, okay? So people had this intuitive idea, and after a long time, physicists were able to give energy a rigorous definition, and that's what we're going to do in this introductory video, all right? Before we do that, we have to introduce a second definition of something called work, all right? So let's define work. Work is it's with regards to a force that moves something, okay? Work is the product of displacement and a component and the component of a force in the direction of the displacement. All right, so that's a lot of words, but let's quickly do an example to make it more concrete. All right, so suppose we push the box across the floor. Okay, so let me make a diagram of that. Okay, and let's say that we pushed with 100 newtons, and let's say that the box moved 5 meters. Okay? So the work is the product of displacement and the component of a force in the direction of the displacement. So force is in the direction of the displacement, which is to the right. So work is force times the distance moved, delta x, the displacement, okay? So 100 times 5, so 500. And the units are the units of force times displacement or distance, so 500 Newton meters, apparently, right? And in honor of a famous scientist that studied energy called Joule, we refer to these Newton meters as 500 joules, okay? So pushing this box with a force of 100 newtons, 5 meters, that gives that you performed 500 joules of work, okay? Joules is Joules for your information. All right, now why did I specify that you had to use the component of a force in the direction of displacement? Okay, well, that wasn't the only force involved, right? The box was under the influence of the applied force, but there was also gravity, okay, whatever that is. The box also was experiencing the normal force from the ground, okay? Those forces did not do any work, okay? Why is that? Well, the displacement was horizontal and those forces were vertical, so they don't have a horizontal component. You see that? So those forces didn't do any work, okay? If you applied a force at an angle, okay, let me do an example of that. Suppose that maybe you have a pack on the ground, okay, and you have a horse pulling it with a rope, via a rope somehow. So let's say here's some pack, some box, whatever, some supplies, and you tied it to a rope, okay, and at the other end of the rope you have a horse, all right, and let's say that rope happens to be maybe at 30 degrees, okay, and let's say that the horse is pulling with 1,000 newtons because it's a strong horse, okay, and let's say the horse pulled this box for 10 meters, okay, so F of the horse is 1,000 newtons, and the displacement is 10 meters. Okay, so what is the work? The work is the component of the horse's force parallel to the displacement. So why don't I put little parallel symbols, two little parallel line segments, okay? So there's our formula for the work, okay? To calculate the component in the direction of travel, the horizontal component, in this case it would be 1,000 times the cosine of 30 degrees, right? And then we multiply that by 10. So 10,000 times the cosine of 30, or root 3 over 2. So apparently 5,000 root 3 joules is the amount of work that this horse would do pulling at this angle. Okay? And still in this example, the gravity and the normal don't do any work. Okay? By the way, think about a centripetal force. Think about the force that keeps something moving in a circle. Okay? The motion is always tangential to the circle, right? And the net force is always towards the center of the circle. What is the angle between a tangent line and a radius to the point of tangency? Okay, you may know that a radius and a tangent line to the same point on the circle form a right angle. Okay, so once again, the direction that something is moving, in that case the direction is always changing, but at every instant the force is perpendicular to the direction of travel. Okay, so a centripetal force does no work. Okay, by our definition of work. Okay, think about that. Okay, now the last thing I want to do is introduce the rigorous definition of energy finally. Okay, energy. The ability of an object to do work. Okay, so now when we say that, wow, that person or that object or that bomb has a lot of energy, now what that means rigorously, specifically, is that it has a lot of ability to do work. Okay, why would a sprinter have the ability to do work? Okay, well, think about an Olympic sprinter or a football player. Okay, somebody that's moving with really fast with a lot of mass, maybe. Okay, so let's go back to the example that we've been talking about. Suppose we wanted to move a box across the living room. Okay, what if we made our sprinter or football player or what have you, what if we made them crash into our box? Wouldn't that move it? So that would apply a force which would cause a displacement. And so there, don't you have work? Okay, so objects in motion simply by crashing into something could do work, right? Okay, on the other hand, think about a bomb. Okay, if I had a bomb and the bomb blew up, that's obviously going to move stuff, right? Okay, so a bomb also has a lot of energy. Okay, if I have let's say that I had a bunch of trash. Okay, I don't know what trash looks like. Let's say it's this red blob, and I wanted to compress it. Okay, so I want to apply a force down, a force on the trash and make a displacement to move it down. Okay, on the other hand, what if I put that pile of trash right next to a cliff? Okay, and at the top of a cliff, I intentionally chose the cliff where there was a big boulder hanging right off the edge. Okay, all I have to do is tip that boulder, make the boulder fall off the edge, and gravity is going to speed up the boulder and it's going to smack into the trash and compress it, right? So that A heavy boulder high up on top of a cliff has energy too, right? Has the ability to do work. All right. The units of energy are also joules. Okay, just like work.